Hi everyone, I'm going to talk about the Coordinatool. That's a new copy tool that acts as a coordinator, as you can probably guess from the name. Before starting, I'd like to give big thanks to CEA for organizing the LAD and funding both this development and the talk. And while I'm here, also thanks to everyone involved in the Lustre community for making this possible. So we're going to talk about what is a Coordinatool, why am I doing this, then see the internal evolutions and a small demo. So the Coordinatool is a Lustre copy tool that acts as a user space coordinator and gives work to real existing copy tools through an LD preload lib overloading. Let me rephrase this. There's a server that's a Lustre copy tool. It accepts requests from Lustre. It schedules them to existing clients. Then there's an LD preload client library that overloads LLAPA HSM calls and allows using existing copy tools as clients without any modification. Then there's a small administrative client I'll very briefly talk about. This is all still a work in progress. I mean, it's a very young, mostly free time project, but it already kind of works and could be used with a bit of care. We'll see the demo at the end. So why are we doing this? I mean, we're kind of reaching the limits of the in-kernel coordinator. It's not the first time we've been discussing this. There's work for a real user space coordinator in the LU 13384. To give an example of the limits we have, Lustre only allows setting one limit for all actions of each agent. But at CEA, we allow more removes and restore requests. So if there's only restore requests in the pipe and there's more requests than clients are available, Lustre will keep trying to send restores to busy clients that will just refuse them over and over again. We could also do better scheduling, more retries, or whatever we'd like to do. So let's see how this works. I'll discuss a bit on the server, what protocol is used with the client, how the client works, and a bit of the tricky bits I've run into. So the server, it's a single thread process. It registers as an Lustre copy tool. It accepts connection from clients. And then it's basically just one big EPOL loop over the file descriptor we got from the Lustre HSM and client file descriptors. So it just receives and processes requests when it gets them. It answers to requests from clients. And hopefully it won't block in Lustre if I've done things correctly. So it's really not doing much with Lustre. It's just accepting requests it shouldn't block. Let's zoom a bit. An important point of this is how actions are queued. This is important because for the Lustre coordinator, it's a performance bottleneck when there are thousands of actions. The catalog doesn't scale all that well. But the catalog is there, so we might as well use it for recovery if needed. And all the actions in the server will be stored only in memory. Then we'll work with Lustre to rebuild all the requests if required. So before we see exactly how this is in memory, I'd like to remind everyone of a bit of the Lustre types. So there's action items, which are actual HSM requests. An action is restore, remove, archive, or cancel, and there's a feeds involved. And what's important for us will be the cookie that acts as a new ID for the request. We assume this is unique, and it must be. We pretty much ignore the rest, we just give it as is to the real clients. Then there's HSM action lists, which are a bunch of action items. What's important for us here is that the items don't actually contain some flags. It doesn't contain the archive ID, it doesn't contain the FS name. So we must be careful when we store the items, either to unreached items or to store them in one list that is only specific to archive IDs and flags. So we're going to do the later. So what kind of requirements do we get from this? What I just said, that queue must group by identical flags. For now, the code only handles a single queue, but it's structured to allow multiple queues, and when it sees a request, it gets the queue with proper arguments. So it's just a matter of reworking the things to allow multiple queues. It's very simple modification. So next requirement we get is that if we see cancel, for example, we need to quickly find a request by its cookie. So we need some quick lookup. It's used for cancel, and it's also used for deduplication that we'll need for a recovery mechanism. So if someone tries to queue an action we already know about, we'll just ignore it. So what does this give in practice? So it's implemented. We use lib userspace RCU's double linked list, so it's simple list head as we see in the kernel. There's one queue for each type of action, for each flag and archive ID. So we have a restore, archive, remove queues for each of these. If the request has been sent, we also have lists for the client. So it's either in the restore, archive, remove queue, or in the client list. Then we have lookup tables as glibc h table. There's also one per archive ID. And each action in memory also contains a pointer to the current client if there's anyone unlinked hit. That's useful for cancels. And a pointer to queues if the action has been sent to a client and the client dies, we need to know where it was to requeue it. We also have a copy of the item itself, obviously, because we need to send it. So how is it sent? This client protocol is a simple JSON serialization, so it's mostly human readable, not very agreeable to read, but possible. The server only replies to clients, so with simple RPC, there's no sudden request from the server to clients. So the clients basically have the receive callback, HSM receive, and we give work when there is. Then the code is shared as much as possible, both between the client and the server for all the JSON stuff that's common, and between both clients we have. So now a new client would only need to implement a few callbacks and can be done in a few hundred lines of code. The protocol implements just a few requests. With this for I'm able to do everything I wanted to do. There might be a bit more later, but for now it's enough. There's a status query that's really just administrative. We get some statistics, the number of pending, running, and processed action for all remove, restore, and everything. Number of clients connected and stuff like that. There's most important request that's give me work. The client will say, hey, give me work. I can handle this many restores, this many archive, and everything. So that's one of the specific points we wanted to improve over the Lustre protocol. Then there's a done request. That's basically the client saying, hey, I finished this, so we can handle it and it more work. And there's a queue command that's a bit specific. It's basically pushing HSM action list like we would do from Lustre API receive. It's used for recovery. We'll see that in more details later. So we'll get into the client. The LD preload client just overload a few LLAPI HSM functions. So we have copy tool register and register, obviously. This allocates our own copy tool private data with magic that's different from Lustre, so we hopefully cannot mix the two. And if we call, if the copy tool calls LLIP HSM functions that we did not overload, it will hopefully fail. It does very similar things to the normal registers. That is, it connects to the server, it opens a root, Lustre root, and .lustre/feed file descriptors. We'll use them later. And then we implemented the receive call. That's just sending receive and wait. And the magic happens in action begin and action end calls. So I found out we can actually just call the real ones and let Lustre and means the Lustre API do all the work. We just extend the copy action private with some fields specific to us, like where to send the done request at the end. I will also overload copytool get FDs that would just return the TCP file descriptor, because, well, if I do that, we could actually chain the coordinators. That would be pretty useless, but it could be possible. And that's it. It's all the calls we need. We don't actually need more than this. So why does it work? So calling action begin actually works on a different client. Lustre doesn't care if the client is different between the ones that actually receive the work from HSM receive and the one that actually does it. This is very good. I first saw that the Coordinatool would need to open and create a temporary file, send the temporary feed, then let the client do the work, then when the client is done, do the swap on the Coordinatool. It's not actually needed. That's very good. In the same manner, progress and other call mostly just work as is. It doesn't need anything specific. It depends on a borderline bug, that is that action begin actually takes a copytool private struct but doesn't check the magic. So we need to be careful that the MNT FD, that's the root of the file system, and the open by feed FD, the .lustre/feed file descriptors are the correct offset in the struct. It would probably be better to use the same magic as Lustre if Lustre starts checking this, and that would allow for checking the offset, but in this case it would not protect us from calling unimplemented LLAPI function, so I'm a bit mixed feeling on this. But it does just work. Then, well, that's good. Okay, we have a simple administrative client that's really just getting stats or debugging or testing, so we can actually request work and dump in std out. That's not very useful. It doesn't actually acknowledge the work, so when the client disconnects, the server will just requeue and the work is not lost. It's very simple. To illustrate that what I was saying with common code, specific client-specific code is only just 200 lines of code. It's really just very, very simple. That's enough to make a client. The LD preload client is actually not much bigger than this. I mean, it's only just calling a bunch of LLAPI functions. So let's get into the tricky bits. Now I've said everything was simple. What happens if the server starts? What happens if the client disconnects? The few Lustre turnings I've needed to fiddle with. If the server restarts, because actions are only queued in memory, and well, Lustre doesn't handle a copytool disappearing really well. If the request has been sent, it assumes that the request has been sent and it never sends it again until the timeout. It also means that if we try to actually commit on disk or whatever, there's always a window between the request have been received, sent to the client, and the request have been read from the client on the client. So it's not possible to make something robust. There is no acknowledgement that the request have actually been acknowledged. So it's really better to rely on the server. So that's what we do. The server actually lists all the requests that are actually active, as in have been sent to copytool. We can just parse that file and sending with a Q command. So whenever the server starts, we just need to go on the MDT, check that file with lctl get param and queue all the work again. There's another problem that's if the server restarts and clients were already running stuff, if we just requeue all the work, we would risk duplicating that work. So clients that are handling a request would be sent the same request again that the Coordinatool doesn't know about. This is not done yet, but the client could write files in the file system when they start doing work, and the server would just read this file in startup and gives each action some grace period, so it's some timeout, for example, we need to implement a kind of timeout over this, but it would work. I assume Lustre would be good enough to allow multiple actions actually, because when you do the action begin, it must take some lock, and that would just block the second client, and when the first client finished, the second client will realize there's no work to do. But I haven't really tried this well enough to rely on it. It requires a bit more testing here. What happens when the clients disconnect? Currently, it just recruits its processing actions immediately. It could be interesting to give a grace period to reconnect, but we all know that on HPC systems, TCP never fail. So, is there any point in that? It would need to reclaim running action and connect. It would need to trust the service manager to not have duplicate on the same host. And well, I mean, it's not the most critical thing right now. It will be done later. Then there's a few Lustre tunings we need. That is, normally requests are meant to time out when a client is slow, but if we just have a huge queue, there's no point in timeouting fast. Actually, Lustre had a few bugs when request timeout, so it's better to just make a very, very big active request timeout and make sure that in 30 days we will handle all the requests. We also want to send the request as soon as possible, so a short loop period and a high max request. This is actually what we use in production already, but it could be made higher, I guess. It's good enough to absorb the flow of prediction for us. So that's it for the internals. We're going to talk about what's next. Very briefly, finish all the to-dos that have been listed earlier. Most importantly, server restart and HSM cancel. And if we get these two, it's probably good enough to start using for real. It would need way more tests. What I was saying earlier, what happens when two clients get the same request in parallel, what happens when server restart, what happens when the Lustre server restart, what happens on all kind of different fun cases that will be very fun to script. CA is giving me a headache. Then we can actually start improving the scheduling. Right now we got just basic restore is more important than the rest, like the coordinator does. We could imagine checking file owners and not letting a user hog all the agents. We could check file locality on tape and group requests by locality. We could imagine whatever we want to do. We could add a few more commands like dump all the requests for debugging, lock and unlock if we want to temporarily suspend new requests. It's something we want to do from time to time. Then there's a big migrate from Coordinatool to Lustre userspace API. The rest of the server, all the scheduling logic and the LD preload client could be used as is. Well, there's work. If you want to help, welcome, please do. Let's get on to it with a demo. So, we have single, I'm doing everything on a single machine for simplicity with the same file system mounted 3 times. So it kind of illustrates that we have multiple clients. I'm going to start the Coordinatool on one client. So it's registered a Lustre Coordinatool, it starts the main loop. If I just go here, Lustre is empty and create a file. If I send HSM archive request on this file, the Coordinatool gets it. Then if we start POSIX Coordinatool, it will get the requests, it finishes the requests, and the file has been archived. So now if we, for example, HSM reads the file and try to read it, it will get a restore and the file is restored, so it's great. I can show a remove that works as well, everything works as planned. What else is there to see? Yes, so right now if the server restarts, so I just sent a new archive, is queued on the server, then we kill the server and we start it again. If I start the POSIX copy tool again, it won't get it. The server currently doesn't know about it. So we can just queue the action again. So what I'm doing here is lctl get param mdt hsm active requests, and using the client with the queue option, it sends the requests and it unqueued it. So here the POSIX copy tool was running and it took the request right away. But if it hadn't been, this is deduplicated. So if we try again, I sent a request, I'm killing the client, I'm restarting the client. It's unqueuing the first time, and it's properly seen as already unqueued the second time. Alright, so well, that's about it for now. It works. It could work with multiple clients. Everything already works from this point. So please give it a try, comment. The code is on my GitHub. More tests is more than welcome. Filling issues, pull requests, anything you want. And I'm open to taking questions on the chat. Please show interest. Hi. Okay, thank you very much. Bye.